we're going to talk about homework number 7, in which we're considering this equilateral triangle and the action of the group of symmetries of this triangle, so that's the group D3, acting on the numbered corners of this triangle. So let's have a look at what happens. We've got elements E, A, and A squared, which are the rotations. So A is rotation anti-clockwise, that's this way, by 2 pi by 3. And B, the BI's are the reflections in these 3 lines. So E obviously leaves everything in the same place. So what does A do? A rotates ourselves kind of one way, that way. So 1 goes to 2, 1 goes to 2, 2 goes to 3, and 3 goes to 1. And if you do it twice, 1 goes to 3, 2 goes to 1, and 3 goes to 2. Okay, so that's those. Now, the BI's, B1 is reflection through this line, the one that goes through the corner 1. And if it's reflection through this line, it's certainly going to fix 1. Right, so B2 is going to fix 2, and B3 is going to fix 3. And then what it does is it swaps the other 2 corners. So here 2 and 3 get swapped, here 1 and 3 get swapped, and here 1 and 2 get swapped. So that's what the final table should look like. Now if you think about these as permutations, you can write down, this is like 2-row notation for the permutations, right? So if we wrote these down as in a product of disjoint cycles, here we get the identity. Here we have 1 goes to 2, 2 goes to 3, and 3 goes to 1. Here we have 1 goes to 3, 3 goes to 2, and 2 goes to 1. Here we've just got the transposition that switches 2 and 3. Here we've got the transposition that swaps 1 and 3. And here we've got the transposition that swaps 1 and 2. And so the point is that using this action, we have found a way to take an element of D3 and produce an element of S3. So here we've got elements of D3, and each one of these is going to an element of S3. So under this map, what we've got is E goes to E, A goes to 1, 2, 3, A squared goes to 1, 3, 2, B1 goes to 2, 3, B2 goes to 1, 3, and B3 goes to 1, 2. So this is a map theta. I hope that red is just about visible. And so what we have to do now is to try and show that that theta is a group homomorphism. So what do we have to do? We've got a map theta that goes from D3 to S3. That means that it takes each element of D3 and produces from it an element of S3 in this way. So what we have to do to show it's a group homomorphism, well, we're trying to show it's a group isomorphism. We have to show that it's, first of all, a group homomorphism. And we also have to show it's a bijection. Now, to show it's a bijection, we have to show that every element of S3 appears in this list, and moreover, that every element appears only once. So, well, let's have a look. S3 has 6 elements. We've got, 6 elements here, and they're all different. So that definitely has to be a bijection. This is clear because each element of S3 appears exactly once. Now, technically what we have to do is show that it's injective and surjective, but because this is a very small list of things, we can just have a look and see that everything appears once. To show that it's a group homomorphism, what we have to do is show that for all A and B in S3, theta of A times theta of B is the same as theta of Oh, that's a terrible notation. Let's try that again. For all x and y in D3 is what I'm trying to say. Theta of x multiplied by theta of y is the same as theta of xy. And so technically you have to do this for every single pair of elements x and y in D3. So for example, we could try doing this to a and a squared. E.g., we need to say that theta of a times theta of a squared equals theta of a times a squared, which is a cubed. Well, what is this? Theta of a is 1, 2, 3. Theta of a squared is 1, 3, 2. And we're trying to show that that's theta of a cubed. Well, what's theta of a cubed? The a cubed is just e, right? And so we're trying to show that that's the same as e. Well, what's 1, 2, 3 times 1, 3, 2? Oh, it's the identity. So that's correct. And actually we have to go through and check every single one of those. Now one way we could do that is by drawing out a big multiplication table, both for D3 and for S3, and checking that everything matches up. Another thing we could do is just write down every pair, and that would be one way of doing it. Let's do another example, just so that we can make sure that we've got the hang of this. So let's try doing theta of A multiplied by theta of B1. That's supposed to equal theta of A B1. Well, the first difficult thing is what is A B1 in the first place? Well, what's A B1? Perhaps I shouldn't have taken the triangle down. So what does the triangle look like? It had 1, 2, 3, so that's the line B1. That's the reflect. We're going to reflect in B1 first. So if we reflect in B1, we get the triangle the other way up, right? So then we get 2 up there and a 3 down there. And then if we rotate once, then what we get is a 1 over here, a 2 here, and a 3 there. Okay? So let's have a look. What's that the same as? If we started with the triangle, like that. So what's this the same as? Well, we fixed 3, and we've swapped 1 and 2. So this must be the same as B3. So we're trying to get this to equal theta of B3, right? And theta of B3 is 1, 2. What about over here? Theta of A is 1, 2, 3, and theta of B1 is 2, 3. And what's 1, 2, 3, 2, 3? Well, let's see. 1 goes to 2, 2 goes to 3, and then goes to 1. And 3 goes to 2, which then goes to 3. So indeed, those two are equal. So you have to go through every pair and work out that theta of x times theta of y equals theta of xy. And notice that this is an element, each of these, that's an element of S3, and this is an element of S3. So over here, on the left, you're doing a group multiplication in S3. Over here on the right, we're doing xy, right? That's a group multiplication in D3. So here you're going to have to do a multiplication in D3 and then apply theta to it. Now one thing you might notice is that it's actually, well, I think it's easier to multiply permutations like this than it is to multiply the symmetries in D3 straight off. And that's one of the useful things about group isomorphisms, that instead of, for ever in the future, now that you know that these two groups are isomorphic, if you're trying to multiply these two, you can just go over to S3 and multiply them in S3 instead, where it is perhaps easier. Right, that's the end of that.